right, so in our derivative notes, the first thing that's important is for you to understand what these different notations mean. And we've seen them all since we first started talking about derivatives, whether we call it f prime or whether we call it y prime or the change in y compared to x. And as far as I'm concerned, we can keep going because we can talk about the derivative as the slope of the tangent line. And then we ended up talking about with integrals, you can call something the derivative as something else and call it a completely different name. So g of x or h of x or q of x or whatever you wanted would definitely still work. But for the most part, the change in y with respect to x, and we can talk about how we found that by looking at y1 minus y2 compared to x1 minus x2. And we found the limit as that change in x approaches 0. And that's how limits and derivatives were tied together. Because if I had a graph that looked like this, and I wanted to find the slope, finding the rate of change on this line versus this line gives me that understanding where if this distance between my x coordinates became small, that was that part of that change in x approaching 0. Way back to thinking about derivatives. So the rate of change of a constant is 0 because a constant doesn't change. So have that in the front of your brain. And you know, because we've been doing that, but that constant doesn't change. That's why we talk about it being a constant. When we talk about that power rule, that coefficient that's out in front, he just hangs out. But we bring down that exponent, and then we take one away. Compare that now to how we do with the integral. Our product rule is where we talk about the first times the derivative of the second times the derivative of the first. And I know I'm guilty of doing that in whatever order fits or suits, because it's all multiplication that's commutative. So if you do it in a different order, you're fine. But when it came to the quotient rule, that was the one that I found myself doing what? Yeah. That jeopardy. Low D high minus high D low. Square the bottom and away we go. So our chain rule is every single time that we approach this, we had an inside function and we had an outside function. So when we're talking about our derivative, this original function is going to be to the 1 less power with n out in front, but then I need to find the derivative of what's inside. And whether you think of that as a composite function or written that way, up to you. Now, as far as our exponential, logarithmic, and trig rules, they're all on the back. And those are the ones that if you use them enough, they'll commit to memory. But if you don't use them enough, like a Post-it note on a car going down the highway at 106 miles an hour, gone, right? So if you ever need those rules, again, there they are, or there'll be something that you can Google. For the final, you'll have a sheet with these on them. So anything that's on that back chart, your trig, your log, natural log, and exponent, we'll go ahead and give you those. So what you need to know for the final is everything on up. Sound okay? All right. So the way tic-tac-toe works is partner A, partner B. Last time we did partner A was the oldest. This time we're going to do partner A is the youngest. Partner A, listen first, then do. Partner A chooses a square. Both partners do the work. They compare answers. If partner A and B agree, chances are it's right. Any doubt, you can come ask me. If both get it right, partner A gets the square. Now it's partner B's turn. He picks, and then they both go. If partner A gets it right, partner B gets it wrong. Partner A gets the square. No harm to partner B. If partner A gets it wrong, partner B gets it right. Partner B gets the square, and it's his turn to pick. If you both get it wrong, nobody gets the square. If you're duking it out, arguing about who's right or who's wrong, come get me and I'll be glad to help out. Make sense? All right, so let's have Nate hop on over, and we're going to have Jaden and Pete be partners, and Nate and Steven be partners. Simon and Jacques, your partners. Ricardo and Kenton, your partners. Let's have Kiara pop back and work with Catherine. And Adrian and Pete be partners. You two and you two, you two. Everybody got it? Decide who's the youngest. And you are partner A. Off you go. All right. First row we were good with. All right. Let's talk about the second row. Quotient. Low D high minus high D low. Square the bottom and away we go. Now this negative, when I go ahead and I multiply that out, might end up creating a sign change. So when you're looking for your answer, go ahead and pay attention to those negatives. In that middle box, I'm going to rewrite my radical as to the 1/3 power. This 1/3 comes out to the 1 less power times the derivative of what's inside. Now, if when I looked at my answers, I realized I needed to simplify more, here's something you need to know. This 2 and this x are in the numerator. This 3 is down here. And this here is 27 minus x squared. And that is to the negative 2/3 power, which means it's the cubed root squared. So if that looks familiar to you when you're doing your work, there you go. Where did I forget my negative? Hold on. Oh, I did. That's another smarty. So this is a negative and that's a negative. You like that better? Is that you? Go. Anything else? Okay. Now for this one, it always helps me identify the product rule if I take the time to recognize, oh, it's this times this. So it's the derivative of the first. No, the first term times the derivative of the second plus the second times the derivative of the first. We went ahead and changed this problem because we didn't do these rules. That's okay. So y prime is equal to the derivative of the sine is cosine, and here we go. And then the derivative of what's inside. This one's kind of fun. 7 to whatever this power is. The derivative of that is 7 to that power times the natural log of the base, which is 7. And then times the derivative of what's inside. How'd you do? Good? Jaden says good. Awesome. I would turn this back over and I would now revisit, maybe put a star or a check mark on ones you're good with, put an exclamation point or a question mark on ones you might need more help with. Maybe add some notes on things you can't remember. I forgot my negative and I forgot my exponent. I'm going to make a note here. Don't forget your negatives. Don't forget those exponents, because those 2 mistakes would cost me 2 problems on a test on something I know how to do. So take a minute and reflect on how you did and write yourself some notes. When we talk about our position, our velocity, and our acceleration, think about when we did that story of the ball falling, and we looked at each time the slope of the tangent line, and this slope of the tangent line is constant. That's why this here is constant. And it's negative because it's falling. So when we talk about this unit, we talk about recognizing where velocity and acceleration play into that position function. And at that time, we didn't know this side of the story. So here, we know that we differentiate to figure out how fast something's going, and then we differentiate again to find the rate of change of the rate of change. We can also integrate back up by finding that area under the curve and going from our derivative back to our original function. Deep breath, Grace. When we have a related rate problem, we introduce a new variable and we do it with respect to time. So we differentiate the whole thing. Time represents what we refer to as a hidden quantity. It's there even though we really can't see it. So that implicit differentiation that we do is where we just differentiate everything and then we go solve for what we need as we go. All right. Related rates is where we're talking about, and again, let's break down what this is. Related rates, we have more than one, and there's some kind of relationship between them. So if we talk about the perimeter of a rectangle is increasing as time goes on, you differentiate the formula with respect to time. When you differentiate this whole thing, the derivative of p with respect to p is equal to 2 times the change in L with respect to time and 2 times the change in W with respect to time. So that's our formula of what the relationship is to how things are changing. All right. With your partner, do me a favor, read through this graph, talk to it, underline, circle, star, highlight what you find important as you talk about with your graphs. Go. So Grace talks about having PTSD from related rates. I have PTSD from this lesson because if I remember, you guys were all firing questions at me and we got so twisted as to whether we were talking about the original graph or the derivative graph or the derivative of the derivative. Remember the second derivative? And we were talking about increasing, decreasing, and we ended up, all of us had a headache by the end of it because I thought I was answering your questions. It turns out I was just confusing you all more. So I like this chart because I'm hoping that what this chart does is kind of helps us organize and structure our conversations. What are we talking about? Our original graph, the derivative graph, or our second derivative graph? Because at the end of the day, anytime you're analyzing a function, you're using the first and second derivative to help you tell the story of your original graph. Your original graph is your situation. That's your story. That's whatever prompted you to do the math in the first place. So when you were in Algebra 2, you were able to find increasing and decreasing intervals without a problem. You trace the function. When is it going up? When is it going down? But when we look at the graph of a derivative, anytime that derivative is a positive value, that's when your graph is increasing. And you can always go back to these graphs and remember that. Here, my derivative is increasing. So this time frame here on my derivative graph is this time frame here. Because when my derivative hits 0 here, that's this point here. So our derivative is decreasing, getting smaller, our rate of change is getting smaller, even when our function is increasing, it's just increasing at a less fast rate. It's slowing down. So if you think about it always within the context of your original graph, you can say I have a positive rate of change. Here it is in the upper half of the graph, but it's slowing down as it approaches becoming zero. Once I start to fall, now I'm accelerating, I'm gaining speed, because both my derivative and my original function, my derivative is negative as I'm decreasing. So when we were talking about speeding up and slowing down, a lot of times we ended up getting twisted between are we talking about our derivative graph or our original graph? When your derivative graph is equal to 0, that's when you have to look for a minimum or a maximum. When your second derivative graph is equal to 0, that's where you look at the change in concavity. So this graph, I hope, makes it easier to structure those conversations, yes? All right, so we have a choice. Ready? A review of finding first and second derivatives and a review of implicit differentiation. A review of marking on the graphs where things are increasing and decreasing, continuous and differentiable. A review of writing down intervals that fit this. On the next page, some multiple choices about increasing, concavity, points of inflection, absolute maximums, matching position acceleration, and velocity. Again, analyzing the graph. Again, analyzing the graph. I would like to start here. How do you feel about that? On our optimization, are we okay with that? Grace, are you going to be okay? Two positive numbers where the product is 196 and the sum is a minimum. Two positive numbers where the sum is 36 and the product is a maximum. Stop and talk to your group mates about how you want to start this problem, and we'll check in. Your mark is set, go.
Does it matter if you solve for X?
So I gotta tell you, my first year teaching this, right? So when I do it next year, I'm not doing related rates and optimization in the same unit. I'm splitting them up. So I don't agree with them being together because I think it muddies the waters. So let's talk about optimization. Optimization is where we talk about finding the minimum or maximum on the graph. So we can go back to one of these other graphs, and if I asked every single buddy here, tell me where your maximums are, you would say this is a maximum. You know that this is where my derivative is going to be equal to 0. You would say this is a local minimum. By definition, a minimum or a maximum is where whatever point on either side of it is higher than it, if it's a minimum, or lower than it, if it's a maximum. Every single person could tell me where the mins and maxes are on this graph. So it comes down to where does the derivative equal 0? Because that's when my slope of my tangent line changes sign. It changes from being positive to negative, from negative to positive, from positive to negative, from negative to positive. what's going on here? Okay, yeah, we can't differentiate that. So is it a critical point? Yes, but can I find the derivative of it? No. So is the graph continuous? Yes, it is. Is it differentiable? No, because of that sharp point. So I can differentiate this graph up until here, but once I get to here, whatever tangent line, like I want you to think about this as a seesaw, I can draw an infinite number of tangent lines on that point. So is it differentiable? No. All right. So now let's go back to this section here. Okay. I'm going to go ahead and write my two. Remember back in algebra when you had two variables, you had to write a system of equations. Now here's the thing. I'm not doing a related rate. One is not changing with respect to the other. And this is why next year I'm separating these two ideas. I'm not putting them in the same unit. Because you can't solve for this if you differentiate this without using substitution and rewriting it in terms of one variable. Now the problem is when we did related rates, you had two variables and we were okay with that. So one of the biggest things that ended up making us twist it up is this the one where I used a system of equations to express one in terms of the other? Yes. Is this the one where I differentiate the whole thing and use the related rates? No. This is optimization. So I'm looking for a minimum. So once I write my two stories, I know that the product of two numbers has to be 196 and their sum has to be a minimum. Those are my two equations. I went ahead and I solved for y in terms of x and I substituted in. Well, now it's time for me to find the derivative. So when I go to take the derivative of x, it's 1, right? And then I'm not going to bother with dx compared to x, right? I don't bother doing that. And then what I talk about here is negative 196 x to the negative second. And I want to figure out where that is equal to 0. Where is my derivative equal to 0? So I have my 1 plus negative 196 over x squared is equal to 0. So 1 is equal to 196 over x squared. When I do my cross products, I know I'm looking for where is x squared equal to 196. Take the square root. And x is equal to 14. Now, here's the deal. We can do some calculator math and see that you could have answered this in algebra. Okay? So when I go ahead and I take my y is equal to, if I had put 196 divided by all the numbers in the whole wide world. Do you remember this trick from when you were learning how to factor? And do you remember how you'd go to the table? Oh, wait, my calculator's on a weird setting. Hold on just 1 minute. Okay, I like that better. Here are all the factors of 196. I am minimizing the sum. So two positive numbers where the product is 196, and I'm minimizing the sum. Look at here, the sum here is 197. Here the sum is 100. Here the sum is 68.3333. Here the sum is 53. Here the sum is 44. Do you see how each time I go down, my sum gets lower and lower and lower? So just by figuring this out, I know that my smallest sum is when the numbers are the closest together. So I've minimized the sum when those numbers are closest together. When it's time to solve for my y is equal to 196 or divided by the value I got for x, which means y is going to be equal to 14 also. Therefore, when the numbers are closest together, that's when my sum is a minimum. All right, let's talk about this one. Two positive numbers where the sum is 36. X plus y is equal to 36. And my product is going to be a maximum. So x times y is going to be a maximum. So because this one has my min or max, that's the one I'm going to be substituting into. Now, it's up to you whether you solve for x or y. It's easier if you go ahead and plug in for y. So y is equal to 36 minus x, so that I know that x times 36 minus x is going to be a maximum. Now it's time to take the derivative. I don't want to do the product rule. It's a lot more work. Instead, I can just do 36x minus x squared is equal to my maximum. By simplifying that, I made it so I don't have to do that math. When I go to take the derivative, 36 minus 2x (36) is equal to 2x, x is equal to 18. So because x is equal to 18, y is equal to 36 minus 18, y is also equal to 18. The interesting thing is if you pay attention to what we're doing, when I'm multiplying my two numbers, their sum is a minimum. When I'm adding the numbers, the product is a maximum. And we played with all kinds of perimeter and area problems. This is where we talked about, remember the new cafeteria tables. If I'm talking about a sum of my numbers, their area is going to be a maximum the closer they are to each other. If you want to see what that looks like on the calculator, where we talk about the two numbers adding together, if I have 36 minus all the values in the whole wide world, and I go to the table of values, when I'm here at 0, when I'm talking about my product being a maximum, 0 times 36, 1 times 35, 2 times 34 is 68, 3 times 33 is 99, 4 times 32 is 124, 155. See how each time I get higher and higher and higher, my product gets bigger. I'm maximizing my product. Optimization is where you're either solving for your min or your max. And it wouldn't be a review of optimization if we didn't talk about some fence and a farmer and some barnyard animal. This time it's chickens. The chickens are getting loose. We need to build a fence to contain them. We have 200 meters of fencing, and we're going to use the side of our shed. So if here's our shed, the fencing that I'm building is going to look like this. So I'm going to have this and this and this. So when I'm talking about how much fencing I have, 2x plus 1y is my 200 meters. And I'm maximizing my area. So x times y has to equal my max. I'm going to stop talking. You, with your partners, see if you can tackle this one. Mark, set, go. All right, so when you look at this one, and you can see that I started off on another route and ended up with fractions and y's, and that's not what I wanted. I wanted to differentiate x with terms of x. And again, I'm not going to find the derivative of my product. I'm just going to go ahead and simplify that and use my power rule. That's the easiest. Once I solve for x, I go back and I plug in for y. And the largest area that we can create for my chickens is if I have a 50 by 100. Sound okay? Optimization. Feel better? So next year, we're stopping the unit there. And I'm testing the kids. So then they don't get it all twisted up with related rates. Because the second half of our unit was when we talked about related rates. And what happens with related rates is instead of dealing with two separate equations and solving for when my derivative is equal to 0, I'm coming up with one equation that tells the story about the relationship between each of those variables. And then I'm differentiating it with respect to time. And I got to read back into problems and see what do I know, what do I don't know, what's changing. And I have to remember if it's changing in a negative direction, then I got to make it decreasing with a negative. All right, so oil spills onto a lake in a circular pattern. So here's my oily spill, circular pattern. My radius increases at a constant rate of 4 feet per second. That is the change in my radius with respect to time, dr dt. That's the change in my radius with respect to time. How fast is the area of the spill increasing at the end of 20 minutes? All right, so I know that my area is equal to pi times r squared. So when I go to differentiate it, and remember, if you don't know what to do here, add that third hidden quantity in with the change in area with respect to time. When I go to differentiate that, remember, pi is a constant, but when it's attached to a variable, it's a coefficient. So I have 2 pi r dr dt. Let's break that apart. Pi counts as a coefficient. So he hangs out just like that coefficient rule. So remember when we did the tic-tac-toe? I don't know where it is. We talked about the tic-tac-toe and we learned about that rule for C. All right. Now this is what's called a related rate because it's showing you the relationship between the rates. There's no more calculus that we need to do. Now it's just plug and chug. Solve for what we need by plugging in by what we had. You just did all of the calculus necessary. No more calculus. All we have to do now is, oh, wait a minute, how fast is the area changing? This is what we're solving for. That area is changing. Now notice 2 pi r is the circumference. How cool is that the derivative of the area is the circumference? I love that story. All right, let's plug in what we have. My change in area with respect to time is equal to 2 times pi, and it said my radius The end of 20 minutes. I need to figure out what my radius is after 20 minutes. Oil leaks in a circular pattern. Radius of the circle increases at a rate of 4 feet per second. So my dr dt is equal to my 4 feet per second. But this is what I now need to figure out what my radius size is at the end of 20 minutes. So if my radius is increasing, if I have my distance is equal to rate times time, my radius is going to equal to its rate, which is 4 feet per second times the 20 minutes. So if I have 20 minutes, do you see how my time doesn't match? So I need to figure out how to make it in the right time. So my rate is 4 feet per second for 20 minutes. Do you see how I need to go ahead and say that 1 minute is 60 seconds? And if you struggle with knowing where to plug stuff in, remember you want your units to cancel out, because that'll give you how long your radius is. So your radius is going to equal to 4 feet times 20 times 60. What's that, 400? 4,800? Yeah? I'm checking it. Yeah. So that's my radius. So that's what goes in for this R. So my change in my area with respect to time is equal to 2 times pi times 4,800 times 4 feet per second. My change in area with respect to time is going to be equal to 2 times pi times 4,800 times 4. 120,637.16 feet per second. Are we okay? Here? 0.16, yeah. So there's my final answer. 12037.1579. All right, whoever said no airplanes, sorry. An airplane is flying on a path that will take it directly over a radar tracking station. Now remember, the airplane's path goes like this, and the radar tracking station is here. Take it directly over the radar. Okay, if C is decreasing at a rate of 300 miles per hour, so DC with respect to time is negative 300 miles per hour. When C is 15 miles, what is the speed of the plane? All right, you ready? It's Pythagoras. A squared plus B squared is equal to C squared. 2A dA dt plus 2B dB dt is equal to 2C dc dt. One of these is never changing, and I can cross it off because it's a constant, and the derivative of a constant is equal to 0. Which one is never changing? Talk to your group mates. Which one do I get to cross off? Mark, set, go. As my airplane flies this way, is A changing? Yes. So he stays. As my airplane flies this way, is B changing? C is Sally. Because the rate of change at B is a constant. So I don't need to worry about him. Let's plug in what we know. So 2A dA dt is going to be equal to 2C, and I already know what dC with respect to time is. You okay if I cancel my 2's out? I'm solving for the speed of the plane. So that's what I need. So somehow I have to figure out these values here. If I'm solving for the speed of the plane, I can only solve things with one unknown. So then I go back up to here where they say, okay, they gave me a value for C when C is equal to 15 miles. So let's come back over here and do a little bit more Pythagoras. A squared plus B squared is 6. And they gave me C squared is 15. So at that moment, when C is 15, I can figure out what A and B are. Well, B is not changing. So 15 squared minus 6 squared. So A squared is 189. A is equal to the square root of 189. So now when I know the square root of 189 times this rate of change is going to be equal to my C value at 15 miles times negative 300 miles per hour. The change in A with respect to T is going to be 15 times negative 300 divided by the square root of 189. A is changing at a rate of negative 327.33 miles per hour. A is getting smaller. That's why it's negative. For optimization problems, we have two equations and we express one in terms of the other. For related rates problems, we've got one equation with both rates in it, and I substitute my known quantities in to figure out what I don't know. Let's just talk about these next couple ones. Without doing them, let's just talk about them. A manufacturer wants to design an open box having a square base and a surface area of 108 square inches. What dimensions will a box produce with maximum volume? My volume is equal to length times width times height. It's easier if you understood how this box was created Oh, it has a square base. Let me change my picture. So when I draw my base of my box, this is X. When I go to find my height, my surface area, meanwhile, has this height to it. That's my box. My volume, my length and width, I can say is X squared times my height. Now there's two ways of talking about these box problems. If I talk about this value here instead and call this my side length minus 2h, that might be easier than adding all of those little things together. Because when you're finding your surface area, it's going to be 4 times x times h plus x squared. Maybe instead you want to say I like it added instead of subtracted. What do you think? 4 of these plus that. I'm okay with that. It's talking about maximization, so this is an optimization problem. If I want to maximize my volume, I want my max x squared times h. So I'm going to go ahead and plug in for h. I'm going to have to solve for h. And plug it in and make it all in terms of x's. All right, let's talk about 7 real quick. This one, apartment building has 250 units to rent, X apartments, then the monthly profit in dollars is given by that. They want to maximize their profits. So you want their profits. This is another optimization problem where you want to go ahead and substitute in. Take the derivative of this and set it equal to 0. Here's an optimization problem. I want to minimize my costs. Take the derivative of this, set it equal to 0. Here's a related rates problem. All edges of a cube are expanding. How fast is the volume? My volume is my side cubed. And that's where you're going to take the derivative with respect to time and substitute in those values. Here's your ladder. A ladder is leaning against the wall of a house. In fact, I think you might have had the same exact problem when we did this months ago. The base is ladder pulled away at the rate of 2 feet per second. Ready? Let's draw it. Here's my ladder. And my ladder is 25 feet long. That's my constant. The size of my ladder is not changing. This height is going to be decreasing because this base is being pulled away from the house. If I call this A and this B, I know that the change in dB dt, my rate that it's being pulled away from the house, is 2 feet per second. Every time that you take the derivative of the Pythagorean theorem, you get less patient with it. Because you know right away you're going to be able to cancel out those 2's. And you know right away something's a constant and not changing. You also know that you're going to have to be doing the Pythagorean theorem to figure out the other side. So if you have a squared plus b squared is c squared, my ladder is 25 feet. When the base of the ladder is 7 feet from the wall, so that's going to be 7, and you need to solve for your a value. And you've done enough of these that hopefully you recognize some of your Pythagorean triples. My a value is 24. My rate that it's sliding down the wall is what I'm looking for. At that moment, my b value is 7. And that's increasing at 2 feet per second. It's no shocker that your rate is going to be negative because it's decreasing. I plug in what I know. I solve for what I'm missing. If I can get my equation with just one unknown, then I'm in business. That unknown has to match what I'm being asked to solve for. Okay, so now they're talking about the triangle. Consider the triangle formed by the side of the house, the ladder, and the ground. Now I need to know the rate at which the area of the triangle is changing. I know that my area is 1/2 times the base times the height. If I want dA with respect to time, I have my product rule. My base times the derivative of the height with respect to time plus my height times my derivative of my base with respect to time. It's your choice what to do with that 1/2. You can pull the whole thing out and has it and be at a factor throughout, or you can keep it with the base. It's up to you. When my base is 7 feet from the wall, this was 25 and this was 24. The rate that the area of the triangle is changing is what I want, 1/2, my base is 7. My change in height with respect to time, guess what? That's what we just found up here. My height is 24. And we knew that my base was moving at a rate of 2 feet per second. So this is a cool problem because you need the stuff from A to answer B. C involves some trick and puts that in front of you. Grace, any better? I'm gonna pretend like you said yes, that you love it.